Well, good afternoon, everybody, and welcome to this SCI 140th anniversary event on Cerium, white light and clean air. So I'm David Burkett, the chair of the Materials Chemistry Group, and fielding questions and answers will be Gordon Armstrong, also of the Materials Chemistry Group. And we would like to present Andy Walker of Johnson Matthey talking about cerium. Its atomic weight is 140. And its uses including white light, LEDs, and catalytic converters. And the talk is going to look at the history of cerium and its applications, illustrating how it's both illuminated and cleaned our surroundings for many years. So there'll be a question and answer session. To ask a question, you just type into the questions box at any time. All attendees are only in listen-only mode, so your line's muted by the organizer. So you don't have to mute anything else yourself. So a little bit about Andy. He's Johnson Matthey's Technical Marketing Director, where he analyzes and assesses regulatory, market and technology drivers for the evolution of the automotive powertrain towards electrification. That covers both batteries and fuel cells. And he also looks at clean energy transition and its implications, both transport and beyond, with clean hydrogen as a key enabler across different sectors. Co-author of over 80 publications, and in 2006 was awarded the Lloyd L. Withrow Medal. He's a Distinguished Speaker Award from the Society of Automotive Engineers, and in 2011 he was elected an SAE Fellow. It sounds like we can hand over to Andy.
Thanks very much, David, for that introduction. As Dave said, I'm Andy Walker, and today we're going to be looking at cerium and what it does. We'll be looking at where it comes from. We'll be looking at many applications, and along the way, there's a few interesting and I hope entertaining diversions around some of the stories, some of the human stories around cerium and its discovery and its applications. As we've said, the Society of Chemical Industry is 140 years old. And so when we look back at its origins, it actually started, its original origins were back in Lancashire, where some chemists in the Widnes, St Helens and Runcorn area considered forming a chemical society. And they initially called it the South Lancashire Chemical Society. And I've been in the South for too long, but actually, my origins, I am a Lancastrian by birth. So there's a bit of a strong link there. And then SCI itself, this evolved into SCI in 1881, involving a number of prominent scientists and entrepreneurs of the day, including people like William Lever, George Matthey, as Dave mentioned. I work for Johnson Matthey, and George Matthey, obviously, his name is part of the organisation that he created with Mr. Johnson, and also a number of other people here like Richard Seligman and Mary Stopes. So some real dignitaries and giants of the field that were involved in forming SCI, and. I also just thought a bit about some of the early meetings of SCI, and the way that they were addressing the key topics of the day there. And an early conclusion of the society came from a UCL professor who was doing some critical work, obviously comparing the temperatures involved in brewing English beers and German lagers, and concluded that lagers generally have less alcohol. So therefore, the main conclusion of the work was that a German can drink much more beer than a Brit. So good to see that SCI, even all those years ago in the early days, was focused on some of the key issues of the day that we should continue to focus on, and of course the friendly rivalry with the Germans that has gone on for 1,000 years or so. So when we talk about cerium, I guess the starting point here is to look at what is it. So first of all, it's a soft, ductile, silvery white metal. You can cut it with sharp knives and things like that. It tarnishes when it's exposed to air. It melts from a relatively low temperature, just about 800 degrees, and boils at 3,400 or so. And it's in the lanthanide, sort of the rare earth series, with atomic number 58. And the reason that we're linking this to a 140-year anniversary is atomic mass of 140. And obviously shown in the periodic table at the bottom of the screen here. Interestingly, it's the only one of the lanthanides that can take the +4 oxidation states, which is very useful in some of its applications, particularly one or two that I'll be digging into in a bit more detail. And in some ways, the rare earth, particularly when you come to elements like cerium, it's a bit of a misnomer because it's the 26th most abundant element on Earth, cerium, and making up 66 ppm of the Earth's crust. And it's around 5 times more common than lead, for example. So a relatively common material and used in numerous applications, as we'll see. So that's the 140. That's the link to the anniversary. That's why cerium. And here's just a quick introduction to what it is. So why is it me talking to you about cerium? Well, the first thing is, when you look on the map here, and these are the old boundaries, obviously, the boundaries that were in place when I was a boy, and Lancashire is very, very strongly there. So the Lancashire link was a good one. The George Matthey one we've talked about. This is a photo I took this morning of my PhD thesis. So preparation, characterization, and modeling of novel ammonia synthesis catalysts. It's a riveting read, and you can buy it from most good bookshops. And within this work, what I did was we had a series of intermetallic alloys, all based on cerium. So cerium ruthenium, cerium iron, cerium cobalt, all of which turns out have pretty interesting characteristics when it comes to making ammonia. So my PhD, which was done in the late 80s, was very strongly focused on cerium and compounds thereof. So, right the way back there, there was a strong link to cerium for me. And then, again, as Dave mentioned, I'm at Johnson Matthey, and one of the main products and one of the main things that I've spent a lot of my career developing is improved car exhaust catalysts. And cerium plays an absolutely critical role in that, again, and we'll dig into that in a little more detail later on. But if we start with the discovery, so it was first discovered as its ore in 1803, and it's the first lanthanide to be discovered. And it was found in deposits back in 1751 by a guy called Cronstedt, who coincidentally discovered nickel. And he felt, because of its characteristics and because of where it was, he thought it was likely an ore of tungsten. So he sent some to a fairly eminent chemist of the day, Carl Scheele, to analyze. And Scheele failed to recognize it as a new element, and the story continues on that in a second. But I promised one or two diversions, and here's one. As I was doing a bit of reading to prepare for this presentation. So there's a number of people out there that have kind of referred to Scheele as the unlucky chemist, and I'm not quite sure that's true, but it's worth digging into some of the things that he did and some of the things that he didn't do during his career. So we've talked about the angle on cerium, but actually his career started very well. So he was working as a pharmacist in Sweden, in Malmo, when he discovered tartaric acid. And winemakers had known about it for centuries, but he developed a technique to extract it chemically, which turned out to be extremely useful. He was also the first person to isolate lactic acid from sour milk and glycerin as well, and then went on to discover hydrogen fluoride and hydrogen sulfide. Now, obviously, hydrogen fluoride is an extremely toxic or extremely aggressive material, can do a lot of damage to people very quickly, but nothing untoward happened there. Hydrogen sulfide, obviously the rotten egg smell, so a very pungent smelling gas. But again, no real issues there. So a good chemist and coming across some really good things, and nothing unlucky so far. And then he discovered oxygen, which was really regarded as his biggest discovery. And he got there 3 years before Joseph Priestley. But he took 6 years to publish his findings, by which time Priestley had published his data, his conclusions, and there on in was very much associated with oxygen. So he missed out on that. And there's maybe a cautionary tale there about looking to get stuff into the public domain, as quickly as possible to ensure the credit goes to the right people. He then came across at least 6 more elements, and they're listed here: barium, chlorine, molybdenum, manganese, nitrogen, and tungsten, but essentially received no recognition for them. He came across chlorine and thought it was an oxide because of the way he obtained it from hydrochloric acid. And it took a while, actually. It took about 40 years before Sir Humphrey Davy showed that the gas that he'd isolated didn't contain oxygen and was actually the element chlorine in its own right. So he was there or thereabouts, but didn't manage to come through with the critical conclusions. He knew barium was an element, but he couldn't isolate it. And again, in some ways, his nemesis, Sir Humphrey Davy, came along a bit later on and successfully managed to isolate barium. He correctly identified molybdenum as an element and indeed named it. But it was someone else who successfully isolated it and got the credit. And the same thing with manganese. So, I think history is littered with some interesting vignettes like this, but quite interesting in that he had a lot of successes in his career, and many of those are enumerated on the previous slide. But a number of things where he got very close, but no cigar, if you will, here. But shouldn't feel too sorry for him. He's got a statue with his name on, a big statue in a park in Stockholm. So he was rightly lauded for a number of the key achievements that he made. So back to cerium. When we look at its discovery and where its name came from, so the people that proved it was a new element was Hisinger and Berzelius. And Berzelius, obviously, again, one of the giants of chemistry, one of the founders, if you will, of chemistry, and say a few more words about him in a second. So they demonstrated it was a new element back in 1803. And they named the new element cerium after the first asteroid in the asteroid belt to be discovered, which was called Ceres. And so in doing this, Berzelius and Hisinger were kind of following what had happened with uranium and Uranus. So a very similar thing there, planetary discovery, and then the next element that comes along was named after that. And Ceres, it's the largest astronomical object in the asteroid belt, and obviously that's what sits between Mars and Jupiter. As I mentioned, it's the first asteroid discovered, and it was discovered on the 1st of January 1801 by Piazzi at an observatory in Palermo. And in some ways, I think it's an interesting date, the 1st of January 1801. You can almost imagine the conversation. You've been out on New Year's Eve, you've had a few beers or a few glasses of wine, you come back to the observatory in the morning, and you claim that you've discovered the first asteroid ever. You can imagine an interesting conversation with his peers or perhaps his partner or whatever. But nevertheless, it stood. And actually, the Ceres asteroid itself was named after the Roman goddess of agriculture, grain crops, fertility, and indeed motherly relations. So motherly relationships. So again, history right the way back to Roman times in the cerium story. I'm stretching it a bit, I know, but come on, a bit of poetic license doesn't hurt. And again, a few more words on Berzelius. As I mentioned, one of the founders of modern chemistry, and is actually accredited with introducing things like rubber tubing and filter paper to the laboratory. So some of the things that those of us that have spent time in chemistry labs over the years, have found invaluable. But it was interesting, despite a strong relationship with Bunsen, Berzelius didn't manage to attach his name to either rubber tubing or filter paper in the same way that Robert Bunsen did to the Bunsen burner. In addition to discovering cerium, Berzelius discovered selenium and was also the first to isolate a couple of other elements. So, there's a number of giants of chemistry working in this field at similar times, and a lot of discoveries are coming through one after the other discoveries, and then the race to isolate and things like that. He's also credited with originating, lots of chemical terms, outlined here. So catalysis, we'll come onto that a little bit later. Cerium's got some cerium and its oxides, got some very interesting catalytic properties, but he also coined the terms polymer, isomer, protein, allotrope. So again, a bit of a polymath across the bio and the chemistry areas, but massive contribution to chemistry overall, and part of that being associated with the cerium story. And again, we've talked about Sir Humphrey Davy, Berzelius, got to know Davy very well. And after a visit to his lab, he remarked, a tidy lab is a sign of a lazy chemist. So something there that has passed out almost into modern parlance. But no need to keep things as absolutely tidy and absolutely scrupulous. Just make sure that everything is safe. And Berzelius as well, a giant of chemistry, and he's gone one further than Sheila here. He's got a big statue in Stockholm, so we're still in Sweden, but this is in a park that's named after him as well. So giant of chemistry and some fantastic capabilities there. When we look at the isolation, it wasn't successful. So despite being discovered back in the early 1800s, it took 70 more years to be successfully isolated. And this was when the American chemists passed an electric current through molten cerium chloride. And again, at this time, a lot of people were experimenting with early electrochemistry, you'd call it, passing electric currents through various things, and these two guys found that was the way to extract cerium in the first instance. And today it's extracted from a couple of ores. Very strong annual world production. A lot of material being pulled out of the ground every year, going into a number of applications, and we'll talk a bit about those in a second. And the main mining areas of cerium are the same as the other rare earths. They are often found together. So we've got places like the USA, Brazil, India, Sri Lanka, Australia, and China. So there's an early application here of cerium in incandescent gas mantles. So the very earliest gas lighting, things like street lights and things like that, depended quite strongly on the fact that there were traces of benzene in the gas, and that's where the bright light came from. But then it was soon established that actually the chemical industry, as it was starting to grow, was a much more sensible place for benzene and a much more profitable place to sell the benzene to. So it was extracted from the gas and then used within the chemical industry. And then the modern gas mantle was one of many inventions of a chap called Carl Auer von Welsbeck, chemist who studied rare earth elements, and also, again, we've mentioned Bunsen's name 2 or 3 times, who'd been one of Robert Bunsen's students. And the kind of gas mantle is shown on here. These are the kind of fabric baskets, if you will, that are pulled together. And then typically you would dip these in the nitrates of, for example, cerium nitrate, the nitrates of the elements that you wanted to impregnate onto them. And then as things burned, some of the cloth burned away, and then you were left with this mantle behind. And in 1891, von Welsbeck perfected this mixture of 99% thorium oxide, or thoria, which had traditionally been used, been the dominant component of gas mantles. But he found that by adding a bit of ceria to it, you produced a stronger mantle, which was important, but it also gave off a softer white light, which was just more pleasing and more effective in street lighting. And as well as being a very good chemist, he was a very shrewd businessman. And so after introducing the new mantle commercially in 1892, it really spread very rapidly. And it says here, even in the first year of its commercialization, 90,000 mantles were sold just in Vienna and Budapest. And then 20 years later, annual production was already hitting 300,000 units. So, a very successful early use of chemistry, optimizing chemistry together to provide street lighting for major cities. street lighting and other lighting. And gas mantles and indeed, the Cerium component was an important part of street lighting until we really started to move to electric lighting as we went through, the first 2 or 3 decades of the 1900s. Cerium has also had some other applications, and since then in the lighting area. So while it faded away as gas mantles with electricity coming in, what we see now is things like Cerium is a really effective dopant in yttrium aluminium garnet, which is used as a phosphor in cathode ray tubes. So some very obvious and important applications there. And in some ways, this sort of takes me back to school days and first understanding looking at primary colours and things like that, and combinations of colours. And the white light, which is really strongly desired for many applications, including things like LEDs, including floodlights and things like that, can be made in a number of different ways, as I'm sure many of you are aware. So one of them is by mixing red, green and blue together. You get white. It's at the central point, if you will, of the red, green, blue matrix. You can use an ultraviolet LED to stimulate a white phosphor. White phosphor is the same kind of stuff that you see inside fluorescent bulbs. Or in a more complex way, but in some ways a more effective way, using a blue emitting diode to excite a yellow emitting phosphor. And by doing this, you get this combination of blue and yellow, which produces white. And when we look at the majority of white LEDs in production today, use a blue gallium nitride LED alongside a yellow phosphor, usually made of cerium doped yttrium aluminium garnet again, where the LED chip emits blue light, part of it's converted to yellow, and then ultimately you end up with the image in the bottom right of the screen of the LED. So a couple of applications already. We'll now move on to some medical uses of cerium, starting off in the early days and working our way through. And here again, a little bit of poetic license just for an interesting human story. Sir James Young Simpson, who was Professor of Medicine and Midwifery at Edinburgh, did a lot of early work on anaesthetics and really spent a lot of his career driving the importance of anaesthesia to get it incorporated into surgical procedures. And you can see from his title on the midwifery side, quite a strong focus of that was on giving birth and help during labour. And actually one of the things that he discovered, this is not cerium, bear with me, we'll come to cerium in a second, but he discovered that chloroform could be used as an anaesthetic. And he got the ultimate in royal approval of this when Queen Victoria used chloroform during the birth of Prince Leopold in 1853. So he spent quite a bit of his time developing and understanding the impacts of anaesthetics and ultimately leading to some very successful applications, as we just mentioned with the case in point. He also, and don't try this at home, this is not a recommendation, but he did conduct experiments on himself and his friends. And there's a lithograph that's shown in the top right here, whose essentially the narrative that goes with it is the effects of liquid chloroform on Sir James Young Simpson and his friends. And the shattered drinking glass used by one of the experimenters is lying on the floor. So again, don't try this at home. But in the early days, when they were trying to figure out the impact and the kind of levels required for effective anaesthesia, this was one of the things that they were doing. And another part of his work was looking at laughing gas. And again, I think it's worth pointing out that laughing gas was actually much used as a recreational stimulant at 19th century parties. So I think, I remember when I was a boy having a tooth out, or a couple of teeth out actually, and they needed to put me under for that. And in order to do that, it was laughing gas that was used to render me sort of unconscious for that. And I think, again, it's a case of there's nothing new under the sun, really, because I think N2O, the little N2O cylinders are starting to make their way back into the younger members of society today as well. God, don't I sound like my dad when I say that. But the cerium link, so Simpson, as well as doing lots of things around anesthetics, also found that cerium nitrate suppressed vomiting and especially associated with morning sickness. And actually, the cerium basis of his discoveries were actually used in over-the-counter medicines well into the last century. So in the Sericol and Novanorin names. So some really good work here, and in some ways quite unexpected that cerium might have such beneficial medical characteristics as was discovered here. And another statue. So this one, Sir James Young Simpson, and this is in Princes Street Gardens in Edinburgh. So all the way through, cerium has been touched by some great scientists, as we've looked for applications for it. The medical uses continue. So in 1995, so I mean, essentially, cerium fell out of favour for morning sickness. Alternative remedies came through, alternative treatments. But then in 1995, it was found that if you had someone with third-degree burns, a weak solution of cerium nitrate was a really good and effective initial treatment for bathing the skin. And indeed, it's now standard procedure in a number of specialist burns units. And then, as is often the case, you make a discovery and find one thing, and then as we look to augment it, one of the other things that's been shown is that if you combine cerium nitrate with silver sulfadiazine, which again is another agent with similar efficacies in treating burns, you can get some synergistic impacts. And this combination is manufactured commercially in Europe as flamacerium and in South America as dermacerium. Now, I don't know about you, but if you get some burns and you're looking to treat it, I think the dermacerium is a much better name, a much more effective marketing name than flamacerium, which kind of sounds as if it's going to make it even worse. But anyway, those two things combined together, and cerium, therefore, again, a critical component in treating people with third-degree burns. The other medical thing that it can help with is reducing strain on the elbows, and this is because ceria is used in self-cleaning ovens. So many self-cleaning ovens will have a ceria coating, and then when you take that to high temperatures during the self-cleaning process, it catalyzes the removal of essentially carbonaceous residues, which is what many of the cooking residues left in ovens actually are. So we've got some, a further, I guess, a move into the catalysis field, but also with as I say, tongue-in-cheek, a health benefit around reducing the amount of strain to elbows from cleaning ovens. Ceria is also one of the two elements that will spark when you strike it. So there's only iron and cerium that will do this. And this discovery with cerium and indeed with iron led to the development of mischmetal alloy, which contains both of them. I mean, the dominant component in mischmetal alloy is cerium, along with some other rare earth metals and along with minor levels of iron. And it's used in flints for cigarette lighters. So, perhaps one can argue not the healthiest of application after some of the other things that we've come across. But there's a really interesting story associated with this around the author Primo Levi, who was author of a book called The Periodic Table and indeed, numerous other articles. And so he joined the partisans in Italy during the Second World War, fighting against the Nazis, but during that time was betrayed. He was imprisoned in Italy and then sent to Auschwitz. So he was a chemist, and his chemistry degree, and obviously, a lot of the journals in those days in the chemistry area, a lot of the literature was in German. He was able to speak German. He had a chemistry degree. And so he was sent to work essentially as a slave at a rubber factory. But while he was there, used his chemistry knowledge to make things like fatty acids, which he taught himself to, which he ingested to help himself avoid starvation. And on the cerium side, he identified and actually stole some iron cerium rods from the laboratory and then modified them and shaped them to make cigarette lighter flints, which he then used to barter. And he's quoted as saying, "This is how we won the bread, which kept us alive until the arrival of the Russians." So, a really strong human story associated with cerium, and indeed, the importance of having a bit of chemistry knowledge, can really lead to some fantastic and in many ways unexpected outcomes. Ceria, it's this polymath of an element. The more you dig into it, the more applications you find. It's also used in the glass industry. So it helps you produce harder, more resistant surfaces. Essentially, it lowers the surface energy of the glass, makes it easier to clean. You can add some ceria to glass and you end up with something that filters out UV, particularly the damaging components of UV, the damaging wavelengths, because most of the damage caused by UV is down to wavelengths below about 400 nanometers, and these are very strongly absorbed by cerium. So here's an example of a commercial product used for lenses that require full UV protection, but you don't require any additional tinting. And really, ceria is known to be the best polishing agent for most glass compositions and used for windscreens, for mirrors. It can also remove fine scratches, scuff marks, things like that. Really, its uses just continue to grow. It's also found uses as a pigment. So cerium sulfide is replacing cadmium red as a non-toxic one of the go-to red pigments. Cadmium red was used for many, many years, and actually when I first joined Johnson Matthey, we had a section that very much focused on developing new pigments, new colours to apply very widely. And one of the managers there was telling me one day that cadmium red was present in things like red Lego bricks at the time. And he said, they'd done some calculations that showed that if your child ate something like 100 red Lego bricks, then there might be raised levels of cadmium in their system. I think if you've got a child that's eating 100 red Lego bricks, you've got other problems on top of the cadmium poisoning. But I think the point is a serious one around the lines of moving from potentially toxic to completely non-toxic benign materials in the pigments area is a critical one, and cerium again has found some applications there. It's also widely used in the chemical industry as a catalyst, so it's used to produce things like alcohols, phenols, ketones. It's used in cat cracking, to break down petroleum. And its catalytic properties are really, what I'll focus on for the rest of the presentation, because ceria has played a key role in the biggest application of catalysis in the world, and in doing so has brought cleaner air to billions of people. And so this story starts in the 1950s in the Los Angeles basin, where photochemical smog was becoming a problem. And the Los Angeles basin, air circulation is relatively limited within it, which really does make it a very easy area for smog formation. And folks had figured out that smog is derived from photochemical reaction, which involves hydrocarbons and oxides of nitrogen. You get these together, and smog can result from it. And they did some measurements. The regulatory agencies did some measurements and showed that certainly at that time, cars were responsible for 70% of the hydrocarbon emissions and 60% of the NOx emissions in the air in that Los Angeles area. So this led them to start saying, well, how can we develop systems to minimize the impact that vehicle emissions are having in terms of things like photochemical smog formation? So they started drafting regulations to say that cars would need to become cleaner and cleaner and cleaner. And as part of that, that kicked off a lot of work and a lot of very good and effective competition between organisations like JM and Engelhard, which is now part of the ASF, and Umicore, to develop catalysts that could be used to mitigate the emissions from car exhausts. And in order to have a reliable test, they developed, it's a very literal story, this one. I mean, essentially, they took a car out with a data recorder and drove it around some of the streets of Los Angeles. So this is based on a real road route in California. And essentially, the test involves, accelerate. So you start the car, then you accelerate it up here, speed up here, time along here. Then you come down maybe a traffic light, and then you go and spend a little bit of time on the freeway, getting up towards 60 miles an hour. And then you've got a number of these different events as you accelerate, drive for a little bit, and then come to a stop at traffic lights, whatever. And then the test, somewhat interestingly, you do this, and then you sit here for 10 minutes, and then you run these first 5 bits of the test again. So this, I guess, somewhat simulates stopping for a coffee or a bagel or something like that on your way into work or on your morning commute. But anyway, so this was the test that was developed in the US to measure the typical, in inverted commas, emissions from cars, because obviously you need to have a test that you can use that's reproducible in order to say, okay, and now we're going to improve things by making this change to the engine, by making this change to a catalyst, for example. And again, just a very brief diversion. This is, until very recently, this was the European test procedure, which, as you can see, it's not based on real world driving in any way, shape or form. So acceleration, bit of a cruise, and then you slow down, a number of those. You repeat this first bit 3 more times. So this is stimulating urban driving up to 50 kilometers an hour, and then some extra urban driving going up to much higher speeds, up to 70 miles an hour, 120 kilometers an hour. But actually quite linear and not representative of any real world driving. And indeed, what we've seen in recent years in this area is very much a focus on moving away from this kind of test protocol towards one that is much strongly representative of real world driving, and that's kind of where we've got to today. So we started developing catalysts within JM, and as I say, other organizations as well. This was our first test car, and the way that the test is run is you have the car on a rolling road. It's called a dynamometer, so the wheels can move. So you put the engine on, you move the wheels so that you can get the acceleration that's required to the speeds that are required. And essentially, the way that it worked initially, I mean, a lot of it is now computer driven. But in the early days, someone would sit in the driving seat and essentially press the accelerator and the brake and follow a cursor that showed how fast or how slow or how the cruise should be and things like that. And at the end of the test, the amount of deviation from the perfect cycle was measured and quantified, and you had to be above a certain score in order to be able to regard it as a valid test. So, somewhat similar to, well, certainly some of the computer games that were around when I was growing up, some very simple ones where you were just following traces on the screen. And the catalysts typically placed under the body of the vehicle, under the floor. Photograph here. This is, the catalysts are coated onto ceramic monoliths with lots of channels through them. So the trick is to minimize the resistance to the flow of the gas that's coming through by having relatively open channels, but making sure that the channels are narrow enough and long enough to ensure a very good probability of contact between all the gas molecules that enter in the front of the catalytic converter, so that they've got a good chance of being converted by the time they come out of the rear. And there was a lot of fuss when things were first going on. A number of people were pointing out that, well, the car companies in particular were pushing back, saying these things they're never going to work, and if they work at first, they'll not work for long periods of time. Don't let us have to go through the effort of developing these systems, adding additional cost to the vehicles and things like that for something that we don't really want to apply and we don't think is going to do much. And actually, we and others did a lot of work to demonstrate that you could have some good durability of these things. So the first long-term test that we did was with Ricardo Engineering, now Ricardo Consulting Engineers, carried out a durability test, 25,000 miles, to prove that the catalyst would survive in the kind of a typical application and could indeed meet the levels of pollutants that were being proposed within the US, the US Clean Air Act of 1970. And you can see some of the headlines on here, the Daily Telegraph, British device rocks the US car pollution case, because it was. The car companies were pushing back quite hard on the regulators, saying, we don't think this stuff's going to work. And we and others were saying, no, we think we can get there, just bear with us, and here's some proof. So if we look at what the catalysts need to do and what they started off being able to do, two different things, essentially this graph shows the impact of the exhaust gas stoichiometry, with oxidizing to the right, net reducing to the left, on the way that catalysts can convert the main pollutants that we're targeting here: carbon monoxide, which comes from the incomplete combustion of fuel, hydrocarbons, again from incomplete combustion of fuel, and oxides of nitrogen, which comes because you've got a very high temperature process and you've got air there. So you've got nitrogen, oxygen, high temperature, they combine together to form oxides of nitrogen, typically NO and some NO2. And the ultimate challenge is we want to be able to oxidize the CO and the hydrocarbons to CO2 and water, and reduce the NOx to nitrogen, all at the same time. So carrying out simultaneous oxidation and reduction reactions, which is very difficult. And we'll come on to how we managed to get there in a while, but certainly the initial acknowledgement was, look, if we can just get something that removes a lot of the CO and a lot of the hydrocarbon, particularly since hydrocarbon is such a strong actor when it comes to photochemical smog formation, then we'll be doing pretty well. So if we can find things that operate in the oxidizing part of the spectrum over here, we should be able to get relatively high conversions of CO and hydrocarbon, and this will be a good step in the direction of improving air quality. So the first catalysts that were applied were indeed oxidation catalysts. These started to go into the market around about 1975, and essentially what we had was the engine was running typically under net reducing conditions, so fuel rich, quite a bit of fuel going into it. And in order to convert in order to make sure that the exhaust gas going over the catalyst was net oxidizing, a secondary air pump was added. So essentially you've got an additional component that's not necessary for the functioning of the vehicle, but is there to make sure that the exhaust gas that passes over the catalyst is net oxidizing, so that we can get the CO and the hydrocarbon to oxidize over this catalyst. And the oxidation catalysts, they were in the location shown again under the floor of the car, based on platinum and palladium in the early days. But then there was an acknowledgement, okay, we should be able to reduce some of the NOx as well. So around about 1978, we saw the introduction of an additional catalyst. So here, again, the engine running under the same kind of conditions. So essentially on the net reducing side, which gives you the opportunity to reduce NOx because you've got an excess of reductants. So we'd have a Nox Catalyst Converter circled in red here, which comes first in the system. And then we've still got this secondary air pump, which then delivers air in between the reducing catalyst and the same kind of oxidation catalyst that we had before. So over the first catalyst, we run the engine rich, reducing conditions, and we can reduce NOx, typically by reaction with CO, inject the air, as we've said, and then we can generate the net oxidizing conditions. So to move towards a system, it's relatively clunky, two separate catalysts, air pump, delivering stuff in between, but we can get, reasonable conversions of all three of the main pollutant species that we're targeting. But then if we come back to this, what we figured out, what the industry figured out, was that if you are trying to do everything at the same time, ideally over a single catalyst, then what you need to be able to do is operate the engine to generate the exhaust feed that's pretty close to this stoichiometric point. Now, fortunately, engines work well under those conditions. So what we saw was the development of systems essentially using an oxygen sensor, which monitored the concentration of oxygen in the exhaust, fed it back to the engine to enable it to adapt relatively slowly. So there were some quite big swings away from this stoichiometric point on both sides, to the net oxidizing and net reducing. But it gave the industry the idea that actually maybe there was a way here to get high simultaneous conversions of all three pollutants if we could get the conditions right. One of the challenges, as I've indicated, is that, here we've got in blue the air-to-fuel ratio. This is of a relatively modern car over the European test cycle. But essentially, it's very difficult to keep everything at this, what's shown in black here, this stoichiometric point where you've got equivalent concentrations of oxidizing and reducing species. So you're spending quite a bit of time in fairly strong transients away from that. And you need to be able to deal with this rather than have lots of pollutants released when you have these large swings. And this really is where Ceria comes to the rescue, because one of the things that Ceria can do, as we show in the equations over here, if we start off with Ceria in its formal +4 oxidation state, when you've not got enough oxygen in the gas phase to react with the CO over the catalyst, the CO can actually pull some of this oxygen out of the Ceria to convert it down to a suboxide. It doesn't go stoichiometrically back to Ce2O3, but this is really just to demonstrate the principle. And then, so when you've got a lack of oxygen, you can pull some oxygen out of this so-called oxygen storage component, the Ceria. And then when you go back to net oxidizing conditions, because you're swinging backwards and forwards, around this stoichiometric point, you can use either NO to reoxidize the Ceria to create nitrogen in the process, or you can use oxygen to reoxidize it, and then the cycle will continue. And a very early example of some data here from one of the earliest three-way catalysts, showing in red the kind of performance that you'd get on a catalyst without cerium, and then essentially the same components, and you incorporate Ceria into it, and you see a much higher conversion of the CO and the Nox. So really strong performance there. And so around about 1981, we had the three-way catalytic converter. We don't have air pumps anymore or anything like that. We've got a single three-way catalyst, and all three reactions enabled over a single catalyst without an air pump. And again, as we've said, whenever there's a discovery, people are always looking at how can we take this further. And so Ceria on its own was used for many, many years in car exhaust catalysts. And then more recently, we saw the development of mixed oxides of Ceria and zirconia. And within these, the zirconia really helps to stabilize the matrix. So you end up with a material, the Ceria zirconia mixed oxides, can withstand much higher temperatures than Ceria on its own before sintering and losing performance, before aggregating and losing performance. But also, if you look at the oxygen storage capacity shown here, which is the amount of oxygen that you can move in and out, in the way that I described earlier, this really does increase, very strongly as you move towards, and then through 20% zirconia through to 80% zirconia, much higher than the pure Ceria that we use as a starting point. So these materials, pretty quickly became ubiquitous in the industry. And moving towards the end here, this is a slide showing that if you have Ceria zirconia on its own, and you need to get to relatively high temperatures like 500 degrees centigrade before you can pull that oxygen out using, for example, carbon monoxide as the reductant. But if you've got some precious metal there, be it palladium in blue or rhodium in red, you start to see very strong activity, even as low as 200 degrees centigrade, to be able to move oxygen in and out. So this precious metal promotion, where the PGM is often used to bring in, for example, the CO will adsorb on these sites and then help it to react with the oxygen at the interface with the Ceria zirconia oxide. So, another really big breakthrough that was driven by Ceria. And essentially what this has done is it's enabled the world to move towards much more stringent air quality and much more stringent pollution regulations when it comes to the emissions from vehicles. So here we're just showing US light-duty vehicle regulations, but showing, out in blue right at the outside, CO, NOx, hydrocarbons, the kind of levels that were out there before we had catalytic technology. And then as catalysts came in and as they increasingly got better, and as the engines got better, more controllable, lower emissions, but also much better control around that stoichiometric point, you can see much higher conversions becoming feasible. And now, instead of having, back in the early 60s, if you had a car and you drove it a mile, you were emitting about 100 grams of pollutant for every single mile that you drove. If you compare that with SULEV, which is super ultra low emission vehicle, the grams per mile, nice American thing mixing the metric system and the imperial system, but nevertheless, we're now much lower than that, around about 1 gram. So essentially, a factor of 100 improvement. And we've done calculations that indicate that if you just take the JM catalysts that are out there, with cerium being a massive part of this, it's present in all of the catalysts that we put on gasoline vehicles today. We're removing 40 tons of pollutants every minute of every day. 40 tons of pollutants every minute of every day. So the kind of air quality improvements that Ceria has enabled by being part of the three-way catalyst is absolutely critical. So I'll wrap up there. So I hope you've enjoyed the little journey here through the history and a number of the applications of cerium. I think I've shown it's a very versatile element with lots of applications. It's been providing light since the 19th century. It's been used in medical applications right the way through to the present day. It's still enabling cleaner air for billions of people worldwide, and it's believed to have played a significant role in saving Primo Levi's life. And with that, I'll wrap up, and happy to take any questions, and wish the SCI a very happy anniversary, a very happy 140th anniversary, and thanks for the opportunity for me to give this presentation.
That's brilliant, Andy. Thank you very much indeed. Gordon, do we have any questions?
Yes, indeed we do, David. Andy, one question that was asked in the course of the presentation, and thank you very much indeed for a very interesting and varied presentation, was when you spoke about the early reducing and oxidizing catalysts for automotive uses. If platinum and palladium were used for the oxidizing catalysts, what was used for the reducing catalysts, please?
So typically, right the way back then, people were looking at things like rhodium, and rhodium is still a component of modern three-way catalysts today. So rhodium is the one that stands head and shoulders above the other precious metals, and indeed above all other metals, in terms of its specific activity for NOx reduction. So they were based on the ones that were successful certainly were based on rhodium.
Thank you. Thanks very much, Andy. Another question arising as we think about the transition from combustion engine cars towards increasingly electric use, and concurrently with it, the emphasis on the circular economy, how recoverable or recyclable are the cerium and the other elements in catalytic converters in these systems?
It's a great question. So historically, a lot of the focus has been on the valuable metals, so the platinum, the palladium, the rhodium, and their use within the catalyst systems. And there, you can see very high, well above 95% recoveries of those. And actually, Johnson Matthey is the biggest secondary refiner of platinum group metals in the world. So we do a lot of work to develop processes to get the highest extraction levels possible of these elements, to minimize the amount of virgin material that needs to be dug out of the ground in places like South Africa and Russia and places like that, to feed the industry. But it's a very interesting question as we look at what's going to happen going forward with increased electrification, where at some point in the future we're going to be able to provide all the precious metals we need for the incoming catalysts from this recycled streams that are coming through, which will strongly minimize the need for additional mining. But it is worth pointing out that as we look at what's going to be replacing the internal combustion engine over time, as we go through the next 10, 20 years, batteries will be the dominant solution in the passenger car space. And there you've got focus around things like nickel and cobalt and manganese and lithium, all of which, again, we and many others are doing work on developing optimum recycling strategies for, because again, as we move towards this recognition that we need to be creating a much more sustainable economy with everything that we do, that becomes part and parcel of that. The other aspect is that for a lot of, for example, heavy duty vehicles, where batteries make less sense in terms of to get the kind of range that's required for long haul trucks, the batteries would need to be big and heavy and therefore expensive, and also take a long time to recharge. The fuel cell systems, are more likely to be dominant there. And there we've got, the use of platinum, which is, the key component, one of the key components in the PEM fuel cells that are used there. So the precious metal story will continue to evolve as we move through the electrification and through the clean energy transition.
Thanks, Andy. And then just one last related question again is one participant wondered, as you were speaking about the move from stoichiometric combustion conditions into lean burn or reducing conditions, typically what effect does introducing a catalytic converter system have on fuel efficiency in an engine? Or does it?
Typically what the industry does is look to absolutely minimize, any pressure drop, any resistance to flow associated with the presence of the catalyst, to ensure that any impact on fuel efficiency is absolutely minimized. I don't have figures off the top of my head because we tend not to make those measurements with and without the catalyst. Everything has to have a catalyst on there in order to meet the emissions regulations. But there's a tremendous amount of work gone on to make sure that we're using the thin layers of catalyst as effective as possible, so that we can minimize the size to which the channel decreases when we coat it. And indeed the substrate manufacturers, the companies like Corning and NGK and Ibiden that make the monoliths that we coat onto, also doing a lot of work to move to the thinnest possible walls, again to minimize it. So it's something that the industry was very aware of in the early days, and we are down towards levels that are close to negligible at the moment.
Okay, Andy, thank you very much indeed. That's everything from the floor for now. So David, can I hand back over to you, please?
Yeah, no problem. So thanks again, Andy, for a brilliant, fascinating talk. Sort of all sorts of snippets I'll remember for a long time. A couple of questions. Do the Cerium zirconia catalysts, do they live as long as the car, or can they be recycled?
So yeah, they live as long as the car, and then at the end of their life, when the car's recycled, then the catalyst moves into the recycling loop.
And if it's not sort of trade secret, where do Johnson Matthey get the Cerium from, or is it just on the spot market? And roughly how much does it cost these days?
Oh, I have no idea how much it costs. I think there's a number of suppliers, because we don't buy it as Cerium itself. We buy it, for example, in the Cerium zirconia mixed oxide form and things like that. Although in some catalysts, there are other forms of Cerium present. But we won't be at liberty to disclose the names of our suppliers.
No, I understand.
And I'm afraid I have no idea how much Cerium costs.
Okay. And a third one is, do you know much about Cerium being investigated for photovoltaics? Does it have any effect with titanium in photovoltaics? The reverse of the sort of generating light.
That again, that's an area that you're well outside my area of expertise and competence there, Dave. So I apologise.
Not a problem. Not a problem.
I did quite a lot of work, years ago on titanium. We did try adding various things to it, and Cerium was one of them, and it didn't do anything special then. But that was very much an isolated part of a specific project. But beyond that, I don't know. Yeah, Gordon, do you want to say a few words to wrap up, since we...
Yes, I was just going to suggest there I might take over from a moment. I'm afraid the gremlins have caught up with us. So on behalf of all the participants today, and indeed David as chair, Andy, first of all, can I say thank you very much indeed for a really interesting talk as part of the 140th anniversary of SCI. I've really enjoyed it. I think everybody else has too. It just remains for me to do a couple of housekeeping items before we go. First of all is to encourage those of you on the call who are not already members of SCI to consider joining us during the 140th year. You can see here on screen there are many different benefits come with membership of and participation in the society. I've been a member of it myself since I was an undergraduate student, so I can heartily recommend it. Also, just to mention, there are a number of other webinars coming up during September, October, and into November. I've just popped up some details of these on the screen here for you. You can find them all on the SCI website, soci.org, and you can register there as well. And then finally, just to say thank you all for joining us this afternoon, for your participation, for your questions. Andy, once again, thank you very much indeed for joining us and for your talk. And we hope to see you all again on another webinar soon.
Okay, thanks very much.
Thanks,
indeed, everybody.
everybody.
Thanks. Enjoy the rest of
Bye-bye.
the afternoon. Bye-bye.